In the last two videos, we looked at the equation that describes the wave motion. In this video, we're going to talk about the wave equation. Now this is different because the wave equation basically defines the set of equations that would define an actual wave, one that follows the properties that we've set up so far, and we looked at the traveling equation. So here I've drawn a small section of chord that a wave is traveling down, and I'm going to look at this little section called delta x, the little section, little length of it, and the mass that's in this distance delta x is just mu, which mu we had defined as mass divided by length, times this delta x, this little itty bitty length. That gives us the mass of that little section. Now, of course, you have the force of tension in both directions. That's going to be equal. If it wasn't equal, then you would have the rope breaking. And you have the two angles that are being made from either side of this string based on the force of tension and the orientation of the way the pulse is going. So this is general. Now we need to look at the forces that are involved. So we can say the sum of our forces in the y direction has got to equal the mass times the acceleration of delta x in the y direction. So we're looking at the forces in the vertical. Well, our sum of our forces is going to be the force of tension times the sine of theta 2 minus the force of tension sine of theta 1. And that's going to equal our mass, which is mu delta x times the second derivative in t. Now we're going to put this in terms of partial derivatives, so it's going to have this little funny d, and we'll explain why we're going to use partial derivatives here soon. So that's our d function of y, or d sub y is our function of the wave. And let's just add for clarity, well, keep it this way. Just remember that dy is actually a function of x and t. That's an easier way to do it, and then I don't have to write so much. And so I'm going to have the second partial derivative d sub y with respect to t. Didn't quite write that the right way. There we go. So now I have these sine values in here, and I really don't want these sine values. I need to find a way to get rid of them. Well, we're talking about some fairly small angle differences here, and I'm looking at this very short separation. So I can take and say, and look at it and say, well, I can look at sine of theta. As it gets close to 0, it's going to tend towards 0. But the cosine of theta, and we'll put this as theta goes to 0, the cosine goes to 1. And I have the tangent of theta is equal to the sine of theta over the cosine of theta. So as theta tends to 0, well, cosine is going to tend to 1, and I can say, well, that just gets me close to sine of theta. So since that's the case, then I can make this substitution and put tangent in here for sine, but that just gets me the tangent. That doesn't really help me out. Well, we have the tangent of theta. If you remember from your class in calculus and trigonometry, the tangent is the change in y over the change in x, and we can relate that to a partial derivative. Partial derivative of d sub y with respect to x. Excuse me, x. And for the moment, we'll just refer to that as some variable s, just to make our writing a little bit easier here. So if I substitute s, because theta 1 and theta 2 here, I want to keep track of that. So I'm going to have, I can distribute my function, or my force of tension out. I'm going to have S2 minus S1 is equal to mu delta x times my partial derivative. It's actually second order partial derivative with respect to time. Now if I divide both sides by delta x, and I have the definition for these difference in s's as being delta s, I'm going to have force of tension delta s over delta x is equal to mu partial differential second order dy over with respect to t. And if I make delta x tend towards 0, then that's just going to be equal to my force of tension times the derivative, the partial derivative with respect to x of s, and that's just going to equal, well, s is the partial derivative of the d function, d sub y with respect to x, so that's going to be force of tension times the second order partial derivative y with respect to x, and that's just going to be equal to mu second order d sub y with respect to t. And I can take and divide both sides by force of tension. And I remember my definition for velocity is equal to the square root of the force of tension over mu. So if I want mu over force of tension, that's just going to equal 1 over the velocity squared. And now I have my final wave equation. Now we can solve this. Well, I should say if you continue in your mathematics career, you would be able to solve this and come up with a whole family of formulas that would solve and be solutions to this equation. A lot of times it's easier just to take an equation and put it into this formula and see if you can make both of them equal to each other. And if you can, then it becomes a valid formula. That would be a wave. So when you would put the equation in on the left-hand side, you have to make sure to take the derivative with respect to x. But in this case, t would be considered a constant. And when you put the wave equation in on the right, you differentiate with respect to t, but you assume that x is equal to a constant. And as you do the derivatives, then you can try to match up the terms to see if everything comes out. Now, you have a homework assignment that has you do just this. You're given an equation, and you need to put it into this equation, the wave equation, and do your derivatives and see if you can come up with, and in that case it's asking for what values of n greater than 2 make the equation valid. So you'll be using this equation, but only from the standpoint of putting in a function to test whether it actually is considered a wave.